Okay, now you got exposed to the vector fields. We're gonna go into line integrals. Okay, we're gonna really introduce the integral sign now. And like I said, knowledge on vector fields is absolutely vital to tackle the line integrals or to understand line integrals, which is why I put it in the vector integral calculus section. Okay, so we've got a lot of work to cover, and we'll just go straight to it, and we'll just start by reviewing some concepts, very basic concepts. Okay, so the position vector, okay, position vector R is equals to x t I plus y t j plus z t k. Okay, so like the position vector, we've got R and t is the parameter. So in this case, t goes from A to B. Okay, no problem like that. So as t, the value of t changes, so it paints the position vector, and the position vector will trace out, like I told you before, a curve, right? A curve like that. Okay, so if we go like that, so you've got x, y, z, or can be the ikk components. It doesn't matter, it's quite interchangeable. So when t is equals to a point here, so t goes from, t is here, the t-axis, A is here, B is here. So t is allowed to vary, and as t varies, the values of the position vector will vary. So let's just say a point here, the vector's here, and then you trace out the point here, the vector's here, the r vector's here, and when it goes to B, the vector's over here like that. And then the curve that it traces out is like this. Okay? And I also told you, or I advise you to pay careful attention that even though it is a curve that we get it from the vector function because the vectors are going from the origin to the curve. Okay, now we're going to introduce a few new terms, and this is absolutely vital because as you study the line integral calculus, direction is very important. Okay, it's very more important than ever as opposed to when you study in two dimensions. Okay, so you got the parameter A over here. Now A is what we call the initial point. Initial point. Okay, and B is what we call the terminal point. Not a problem at all. So we go from the initial point to the terminal point. And there's also an aspect of the direction. Okay, so it's important to know that when as t varies from A to B, so we are going in this direction, we need to take into account, or we need to be aware of the direction of the curve where we are going. So in this case, if down here is A and down here is B, obviously the direction we're going is this way. Not a problem at all. And now if we go from B to A, okay, we are going the other way on the curve. Okay, so the direction is also very important. Now you're gonna get into another aspect such as this, and we're gonna use an example to show what it is. Now let's just say I'm given, okay, and let me just erase this. Okay, so we know the initial point and we know the terminal point of the parameter t. So now let's just say we got the position vector. Okay, let's go with cosine ti plus sine tj plus k, okay, or 1k. Now this is the position vector, and what is the curve that we get? Okay, I already know the curve, I already predetermined it, and the curve that we get is something like this. It's a circle. Okay, if I'm not wrong, it's of radius 1, so it's from 1 to here, but doesn't matter, it's a circle, something like this. Okay, and then the position vector, remember that we are going from the origin, which is 0, 0, 0, to a point on the curve. In this case, it's the circle, point on the circle. So, for example, one such position vector will go from here to here. Okay, it's all on the curve, so it traces up the curve, not a problem at all. So now we would let the initial point be 0 degrees or radians, and the terminal point be 2 pi. So, okay, so let's look at this. Now, just take the graph as an illustration, okay? I believe the direction is correct, but if it doesn't, then never mind, because we're stressing a certain term over here. So t, like I said, I can draw the t-axis over here. T goes from 0 to 2 pi. Okay, so when t is equals to 0, okay, maybe I should stand here. Okay, when t is equals to 0, let's just say the position vector is over here, like I've drawn over here. Okay, then as t changes, as t keeps on going, along the t-axis, as in the parameter changes, we know that the position vector will change. So it's going to go from here, one whole round to the circle, and comes back over here, right? Now when it reaches 2 pi, which is also within the range of t, the position vector is going to be the same as when it's t equals to 0. You just substitute t equals to 0 inside here, you get, I believe it's cos t0, you get a k or I, yeah, correct, ik. And you substitute 2 pi, you're also going to get I plus k. So you're going to get the same vector. Okay, so listen carefully. If within the range of t, okay, there are two values, okay, such as when you substitute a inside, such as when we put in 0, okay, the position vector is going to equal to the same is going to equal to another position vector when we put in another value over here. So when we put in a value of 0, we got ik. Okay, maybe I just put it. So Ra is equals to I plus k, which is also equals to R when we lay 2 pi inside. Now, when you get this, okay, it's to say that as t varies, there are two position vectors which is going to point to the same spot. And when it points to the same spot, what we get is called a closed curve. Okay? Very simple. So t starts from t equals to 0. As t varies, it will trace out the curve. It will go around here like that. And then it will stop over here at the same point where we started. And then that will mean that the curve is closed. Very important concept. That's why I'm laying down all the foundations here. Very important concept, the closed curve. Okay? However, the closed curve means that there is only one point. There is only one point such that this condition is satisfied. There's only one point. So what does that mean? Well, I can best illustrate it over here. Now, let's change the 2 pi to a 3 pi. Okay? Let's change the 2 pi to a 3 pi. And that will mean that if you know your trigonometry or your trigonometry is good enough, we will trace out the curve. 2 pi is going back in the spot here. When we go to 3 pi, we're going to go again and we're going to land on the other side. Okay. And if you would notice, this part of the curve over here has been traced out twice. Okay. Just imagine that you're like running on a track. Okay. You run the track once. And then you're going to run again, so you run the first half, or the half that you run in the first round, you're going to run it again. So you're going to cover, really run there. Okay? So in this case, there are more than one point. You've got a whole range of points at the other half of the circle. So yes, they do meet over here, but it's more than one point. Now if this is the case, it is not called a closed curve. Okay? Not a closed curve. Closed curve only stresses one point. Okay? One point, such that the position vector is the same. Okay, so if it overlaps the curve, okay, if the position vector creates more vectors that overlap the curve, it is not called a closed curve. Okay, that's very important for you to know. All you need to know is whether it's closed or not closed, because those are in the definitions later. Okay, and finally, we all know that. Okay, let me just erase this about closed curves. Okay, and move on to writing the position vector. Position vector t equals to xt I plus yt j plus zt k. Okay, and t is from A to B. Okay, A to B. Okay, so we know this thing over here. Now, we also know that if for t more than A and less than B, okay, if all the component functions are not all 0, so component functions not all 0, okay, RT is continuous, right? We all know that. That means from the range of values from A to B, whatever value of t, the parameter put inside, there's a certain vector, okay? Now, I can be 0, k can be 0, but if j is there, there's still a vector. If all of them are 0, then it's not continuous, because the curve is not defined over there. That's why all is important again, not all 0. Okay, I emphasize again, you can have the I component, and if you don't have the j and k component, you still got the I component. It's still pointing somewhere. Okay, but if you don't have the I component, you don't have the j component, you don't have the k component, it's not pointing anywhere, it is not continuous. Okay, but if it's not all 0, then it's continuous. Okay, and then we would also say that if, okay, in the same range, okay, if this one, the first derivative of the component functions, okay, are continuous, okay, then the curve is smooth. Okay, another term that we must be very familiar with if the curve is smooth. Okay, all these are the new definitions because you really need them for the following theories. Okay, so we got the closed curve and we have whether the curve is smooth or not. So if you got the first derivatives for the y and z the x, y and z component functions, if you have the first derivative, okay, then the curve is called smooth. Okay, within the range of a to b for t.